Hey everyone, welcome to the lecture on trigonometric integrals. So today we're really going to kind of put your trig knowledge to the test. So to start, we're going to go with just combos of sine and cosine, and then we'll jump into secant and tangent. And so for sine and cosine, it's really important to know three kind of foundational equations. And the first one is one that you probably know very well. Sine squared x plus cosine squared x equals 1. And then we also have the sum of angles. So if I wanted to take sine of two angles, say alpha plus beta, then it'd be sine alpha cosine alpha. Sorry, just kidding. Sine alpha cosine beta. Cosine alpha, sine beta. And if I wanted to take cosine of alpha plus beta, it's cosine alpha cosine beta minus sine alpha sine beta. And so the way I remember that is just through a mantra that someone taught me one time for the sum of angles. It's just sine, cosine, cosine, sine. So that's the first guy, sine, cosine, cosine, sine. And then for the other guy, it's just cosine, cosine, sine, sine. So it sounds kind of stupid, but it's really catchy if you practice it enough. And then it's the angles always go alpha, beta, alpha, beta, alpha, beta, alpha, beta. And then for cosine, you have the minus. But however you want to remember that is fine with me. So let's look at example 3.8. So we're going to evaluate cosine cubed x times sine x. So this one's pretty nice and straightforward because hopefully you're already identifying that we have a function and its derivative pair as the integrand. So we can just perform a simple u substitution. So if we let u equal cosine of x, then the derivative of cosine being negative sine x will give us our du up to a minus sign. So I'm going to write negative du equals sine x dx. I always write this third step just so I can get good clarity on what this guy becomes. Like you could just definitely remember to throw in whatever constants you have from your differentiation. But I like to do it this way. So I know that that guy will become negative du. And then I just go ahead and I integrate. So the integral of cosine cubed x sine x dx through u substitution becomes the integral of negative u cubed du, which is just negative 1/4 u to the fourth plus c. And then we backfill on our u, negative 1/4 cosine to the fourth x plus c. Pretty straightforward. Now let's look at something that is perhaps a bit more involved. We have something pretty similar in 3.9, except this time our sine is cubed. But we're still going to think about this in terms of sine is the derivative of cosine. We just need to work the sine cubed part to make this happen. So again, with sine squared plus cosine squared being 1, the idea is to split this. So I want to have a single sine x, and then I'm going to have a sine squared x. And the sine squared x becomes 1 minus cosine squared x. So the single sine x, when you have an odd power of sine, the single sine x is what's going to facilitate getting your du. And then since sine is odd, everything left over, since the power of sine is odd, everything left over will be an even power. And I can always write any even power of sine as 1 minus cosine squared. So just analogously, if I had, let's say, cosine squared times sine to the 5th x dx. I'm not going to do this whole integral out, but the idea is this. You would still peel off a sine x, and then you'd have sine to the 4th. And this becomes sine squared squared, which then would become 1 minus cosine squared x squared. And so in that sense, we get our single sine x, that will be our du, and then everything else is in terms of cosine of x, which will be our u. So let's rewrite the integral. So I have cosine squared x times 1 minus cosine squared x times sine x dx. And if we let u equal cosine of x, then negative du, as we just did above, will be sine x dx. And so when I rewrite this, I get, I'm going to put the negative on the outside. So I would get u squared 1 minus u squared du. And this is really easy to integrate once I push that u squared through. So I'll get negative u squared minus u to the 4th du, which is just negative 1/3 u cubed minus 1/5 u to the 5th plus c. So I'm going to distribute the negative sign and back sub for cosine at the same time. So I'm going to get negative 1/3 cosine cubed x plus 1/5 cosine to the 5th x plus c. And you'd have a really similar flow of work in the other thing I mentioned where it was sine to the 5th. Okay. But what if sine isn't an even power? Like we can't just peel off. Like say for example, if I had sine cubed, this would become sine squared x times sine x dx. And then from here, I would get 1 minus cosine squared x sine x dx. And so now in this situation, I'm poised to let u be cosine, and then my du it's all set up perfectly. That's what being odd, that's what being an odd sign gives you. But here we don't have that. So we have to appeal to a little bit of trig identity and a little bit of algebra. So remember what I said above, we're going to use all three of those formulas. So where to begin? Consider that cosine of alpha plus beta equals cosine, cosine, sine, sine. That is how I remember. Right, so this is what we have. But in the event that, let's say, alpha equals beta, which we're totally allowed to do. We have no restrictions on alpha and beta. They're just two real numbers. So if alpha were equal to beta, then I would have cosine of 2 alpha and now alpha and beta are the same, so this is just cosine squared alpha minus sine squared alpha. That's what that becomes. And then from here, we also know that, like, well, how about this? So I see this and I'm like, oh, cool, I've got sine squared alpha. And I know I can integrate cosine of AX, whatever the angle is, really easily. but this cosine squared guy, he's giving me some problems. So I'm going to convert him into 1 minus sine squared alpha. Because in that way, I'll have a constant and some sine squared alphas, and then I have just a single power of cosine, which is easy to integrate. So what becomes of this is cosine 2 alpha equals 1 minus sine squared alpha minus sine squared alpha. So if I just combine my like terms, I'll get 1 minus 2 sine squared alpha. And again, this is helpful because now I can solve this for sine squared alpha, and I'm just going to get a mix of a scalar, a constant, and a single term of cosine. So the result is that 1 minus cosine of 2 alpha over 2 is equal to sine squared alpha. And let's say they gave you the integral of cosine squared x dx. You would do the same thing, except instead of switching out this cosine squared, you would switch out this sine squared, and so you'd get cosine squared equals all this junk. So the plan is to replace our integrand with the expression 1 minus cosine 2 alpha over 2. So the integral of sine squared x dx equals the integral, I'm going to write it as 1/2, 1 minus cosine of 2x. Right, so it's saying whatever the argument is for sine, just double it. So if I had p over here, this would be 2p. If I had 10x, this would become 20x. And we don't even need a u sub for this. So this is just going to be x minus 1/2 sine of 2x plus c. So for the next example, I'm not going to derive these formulas, although you're more than welcome to if you'd like. We'll just let it be a resource for right now. And we're just going to go ahead and kind of plug and chug with these. So for this example here, we have sine and cosine multiplied together. So we're going to go ahead and use this. And this is another really straightforward integration once you convert it using equation 3.4. So if I have sine of 5x times cosine of 3x, the integrand becomes 1/2 times sine of the difference plus sine of the sum. So this is going to be the difference, 5 minus 3, x plus sine of the sum. And then from here, I just have a really straightforward integration. So negative 1/2 cosine of 2x minus 1/8 cosine of 8x plus your integration constant. So that's kind of sine and cosine in a nutshell. Again, you always want to look at it in the lens of, not always, most of the time you want to look at it in the lens of peeling off a single sine or a single cosine to get your du, and then converting everything else to be either sine or cosine, the opposite of what you peeled off. And then you have a couple little tricks with this set of formulae here, and then kind of when you don't have that single guy to peel off, this is how you convert it into the single term. And it's a really similar process that we're going to use for secant and tangent. So we have the nice property that well, actually here, this is probably more interesting. We know that sine squared x plus cosine squared x equals 1. So if I divide everything by cosine, and simplify, what I end up with is sine over cosine is tan, so this is just tan squared. Cosine squared over cosine squared is just 1. And then 1 over cosine squared is secant squared. So directly from this sine squared cosine squared, I also get the nice formula for secant and tangent, and we'll be using this as well in a very similar way as we did earlier. So, okay, before I was like, oh, I have a bunch of cosines and a sine. Well, sine is the derivative of cosine, up to a plus or minus, so that's a good pair to have. In this instance, what you want to think about is if you had secant x and you took the derivative, you would end up with secant x tan x. So instead of just peeling off a tan, we need to peel off a secant tan. So what happens here is that this becomes secant to the 4th times secant. And that's nice because if I rewrite this, I can now let u equal secant. So that du equals secant tangent, which I already have. So this will become just the integral of u to the 4th du, another really straightforward integration, 1/5 u to the 5th plus c. Back subbing, I get 1/5 secant, 5, secant to the 5th power of x plus c. So that's the idea there. When we can't peel off that secant to join tangent, like we're gonna have to, well, you'll see. We still want a secant tangent out of this, but it's gonna be a little bit more creative. So what's interesting here is that secant to the 4th becomes secant squared times secant squared. So anytime you have an even power, I'll write it like this. When you have an even power of secant, pull out 2 for du is kind of the idea. So if you have an even power of secant and you pull out 2 secants, what you're left over you still have an even power of secant. And we know that we can convert even powers of secant into terms of tangent. So secant squared, so this guy on the right, we pulled him out for the du bit. What's left over becomes, if we kind of come back to our original guy, so secant squared becomes tangent squared plus 1. Which is good because we can combine that with tan to the 6th. So if I rewrite this, I get tan to the 6th power times tan squared plus 1. So we still have our tangents and we also have secants, but in this case, it's going to be secant squared. And if this were a classroom setting, I'd say, well, why is secant squared really good? And then you guys would say, well, secant squared is the derivative of tangent. And I would be like super proud. So in my mind, that's happening. So if we let u equal tangent, then du is going to be secant squared. And again, this is what I want because now I'm ready to just convert all these tans to u's, and then this secant squared dx to du. So I'm going to get u to the 6th, u squared plus 1 du. Another really straightforward integration. So just rewriting the integrand one more time, u to the 8th plus u to the 6th du. So 1/9 u to the 9th plus 1/7 u to the 7th plus c, and then we just need to back sub for tan. So I get 1/9 tan to the 9 plus 1/7 tan to the 7 plus c. So that's the idea.